music, science. It's the Amoeba People Podcast. Greetings and welcome to the Amoeba People Podcast, the show where science and music collide. Collide is a bit on the extreme side, as we like to say. It's really more like a covalent bond, where science and music are sharing electrons of awesomeness. My name is Ray Hedgepeth, the singer-guitarist of the inconceivably nerdy science rock band, The Amoeba People. And today's episode is part 2 of my interview with Dr. Fred Calef of JPL, who holds many titles there, one of them being Keeper of the Maps for the Mars rover missions. Dr. Fred is a geologist, a cartographer, a mega problem solver, which we learned in the last episode is a hallmark of scientists in general, especially those doing science on other worlds where they're solving problems we've never really had to solve before. On the last episode, we talked about his background and how he came to do the work that he does now and what that work involves. And in this episode, we're going to continue to talk about the red planet, Mars, a bunch of stuff about Mars, and we're also going to talk about some of the broader issues facing scientists these days, particularly conspiracy theories and things of that nature. Because, I've often wondered what it must feel like to do good work that you can be proud of, and then to have some dude sitting on a sofa in his parents' basement posting videos that claim every bit of the good work that you do on a daily basis is a hoax perpetuated by the government, the Illuminati, and Elvis, who's still alive somewhere in a bunker, pulling the puppet strings of humanity. But Dr. Fred has some great answers for that, and I'm excited to share that interview with you. And we'll also be breaking down the final 3 tunes in our Geology Folk Song Medley, the epic Geology Folk Song Medley, which appears on our most recent album, The Fossil Record. It's actually the final track on the Fossil Record. It closes the entire album. And since the medley contains 6 songs in total, on the last episode, I broke down 3 of the tunes, Meandering River, Empty Tents in the Valley, and The Outcrop in the Sky. And on this episode, I'll break down the other 3 tunes in the medley, My Darling Talus Slope, the Batholith song, Dig It Deep, and Mighty Fine Hammer, those 3 tunes. So, it's going to be a lot of fun, and we're going to show you, because really our goal with the Geology Folk Song Medley is to get geologists around campfires to sing these songs, because they're fake geology songs, but if geologists start singing them around the campfire, they will become real songs. I can be a real boy. Someday I'll be a real song, won't I, sir? I have no idea what voice I'm doing or what I'm even trying to reference right there. But that's really our goal, is to get people around the campfire singing it. And again, I want to thank all of you who've been downloading our podcast, and we'd like to ask that if you are enjoying this show, then give us a 5-star rating on whatever podcast platform you listen to this on. And that's how more and more people will find out about it, and it'll help us turn up in the search function when people search for science podcasts. You can also share our podcasts with people you know personally and through social media, email, just word of mouth. Letting other people know about it is a great way to get the word out. And so we want to thank you guys for that, because clearly you've been doing it. We've been getting new downloads every month, every episode, and we really appreciate you listeners. There's really no point in doing this show without listeners. So thank you for supporting us and for spreading the word. And you can also support us financially if you would like to on Patreon, if you are so inclined. Okay, let's get into part 2 of A Geologist on Mars with Dr. Fred Calef, and let's begin the episode by jumping into the final 3 tunes in the Geology Folk Song Medley. Okay, I misspoke a moment ago. I said that these songs were not real songs. That's actually not true. Of course they're real songs because I wrote them. I guess what I was trying to convey is that they're not real old folk songs. They don't simply exist in the public domain. Okay, but that's our goal, is to make these, send them off into the future around geologic campfire sites in the future where people are like, I don't know where this song came from. And maybe some, wizened, old, grizzled geologist will say it's from the Amoeba People back in the day. But all right, anyway. So one of the tunes here is My Darling Talus Slope. Now, we needed kind of a waltz because, you always got these old folk tunes. There's always a waltz somewhere. The waltz was very popular for a number of years, so I was thinking along the terms of, like, Oh, My Darling Clementine and, Good Night, Irene. And so My Darling Clementine, there's, My Darling, and I was like, okay, My Darling, what would be the most, like, awkward thing to call your beloved? And the two things that popped up were Talus Slope and, of course, Clastic Wedge. It's hard to imagine anybody being flattered by being called such things. So there once was a girl that I courted, and I called her my Talus Slope. I thought she was my one true love, but she left me and called me a dope. There once was a girl that I courted, and I called her my Clastic Wedge. But my geologic term of endearment finally sent her over the edge. And then we turn that into a duet. So that second line is sung by a female vocalist. So the male voice that you will be hearing in the final version at the end of this episode is Ron Butler Jr. And the female voice is Lisa Bodie Hurd. They're both incredibly talented, amazing singers. So, okay, the next tune came from a geology poem that I wrote. I keep a little notebook of geology poems and ideas and things like that. And so it had no music to it initially, but it seemed to fit here. And it's the Batholith song. It's called, well, technically it's called Dig It Deep. And then parenthetically, it's the Batholith song. So you gotta dig it deep. Dig it down to the pith. If you wanna get down to the Batholith. It's like a giant blimp in the crust of the planet, but you never seen a blimp made of rock solid granite. You gotta dig it deep, dig it deep, dig it down to the pith, down to the pith. If you wanna get down to the batholith. And a batholith, for those of you who are wondering, is when igneous rock hardens underneath the surface and then through erosion and uplift, gets revealed to all of us. So I learned this when I went to Yosemite for the second time in my life, I think. I was, I wanted to know a little more about it. And I discovered it's a batholith, the Sierra Nevada batholith, they call it here. By the way, Yosemite is here in California. And yes, I'm very blessed to be here in Southern California. You can drive 7 hours north and hit Yosemite, and you can drive 7 hours east and hit the Grand Canyon. So two of the most amazing places. And both of those places, the batholith and the Grand Canyon, are on the fossil record. So, or make appearances on the fossil record. Okay, now on to the final song. And this is not the order that the songs come in the medley necessarily, but this is definitely the last song in the medley. So I wanted something like, because I was we modeled the recording after a couple old folk recordings, like the Weavers live at Carnegie Hall. So we added in an audience and laughter in the appropriate places and things like that to make it extra cheesy. And this final one, we needed like a rousing finale, and I realized a lot of the old folk singers back in the day, they were trying to rouse people towards good things, like change and civil rights and things like that. And so I thought, well, what would geologists want to be rousing people toward? And proper identification of minerals, I think, in rocks might be their kind of mission statement there. So anyway, so this is Mighty Fine Hammer. Well, it's a mighty fine hammer ringing through the canyon. Oh, it's a mighty fine hammer ringing across the land. Well, it's a mighty fine hammer ringing from the mountain, ringing out to every woman, child, and man. Oh, no, we're not going home. Oh, no, we won't be moved. We'll keep chipping away. We got something to prove. Oh, no, we won't be satisfied. We'll hammer around the clock until we learn that mineral composition of the rock. Until we learn that mineral composition of the rock. until we learn that mineral composition of the rock. There you have it, Mighty Fine Hammer. So, I just imagined, old folk singers on stage or geologists around the campfire, getting everybody, we're going to do this. We're going to make it happen. We're going to identify the minerals in this rock. Okay. And thereby identify the rock as well, or therefore, I guess. So, all right. So those are all the songs now in the Geology Folk Song Medley. So, let me see if I can list them all from memory. So we have My Darling Talus Slope we just hit. We just did the Batholith song, Dig It, Dig It Deep, and Mighty Fine Hammer, plus the 3 that we did in the last episode. So if you want to hear me break those down, you can go back and listen to that one and hear that great interview with Dr. Fred Calef. And at the end of this episode, we will hear the full recording of that song, made to sound like an old folk concert at Carnegie Hall. The Weavers live at Carnegie Hall. But this is the Amoeba People with our friends Ron Butler and Lisa Bodie Hurd, the wildly talented duo who make this song such fun to listen to. So that will be at the end of the episode. And before that, though, we have this fantastic interview with the amazing Dr. Fred Calef. So let's get back to part 2 of my interview with Dr. Fred. Okay, I want to start off the interview just by reminding those of you out there who have listened to the previous episode, part 1 of my interview with Dr. Fred, that there are spots in the interview where I will stop and you will hear a theremin sound like this. And that is because those are the spots where we pulled out lines from his interview and created a new album for Dr. Fred on double theremin. That commercial is in the last episode as well, so if you've not heard that, please download that episode and listen to that and get a good chuckle out of that, will you? So that's first off. And then second off, the question that I began this segment with was, how do planetary scientists transfer the geology that we know about Earth, the geologic information about Earth, to another world? How easily does that transfer, and what difficulties does that pose for scientists?
Planetary science definitely... you have to challenge all your concepts of geologic understanding. Mm-hmm. Earth is a water-dominated planet. Thereby, most of the things, not all things, but a lot of things are dominated by water. Mm-hmm. The shape of hills and mountains, stream valleys and channels and flood deposits and all those things which are very much on the surface. Mm-hmm. So then you take that and you go to, let's say, the moon. Uh-huh. Moon, no water.
Right.
Now they talk about, ice and the surface and all that, but
not in a way it would affect the surface the way water here does.
Exactly. Yeah. It's kind of like water that's adsorbed to the surface, or it's formed in place in the rocks as they are. It's not like there were stream channels and lakes and oceans. Like, no one's saying that.
Right.
They're saying there's some places where water molecules can collect and then just kind of like make ice in place. Mm-hmm. It's not ice that moves. It's not carving glacial valleys. It's just sitting there.
Yeah.
So that, the moon is like the polar opposite. Super dry, covered in impact craters. Mm-hmm. So everyone thinks like, oh, Earth is like the model for the solar system. No, the moon is almost the model for the solar system. Impact cratering, which is where the meteor comes out and lands, becomes a meteorite, forms this big impact crater like Meteor Crater out in Arizona. Mm-hmm. That's what most of the moon is. It's just impact cratering geology. And if you look at planetary history, more or less over the lifetime of a planet, impact cratering is almost the dominant geologic process. It really is for most planets. Especially with those without atmospheres.
Right. So this is why they often say that, like, studying, places like the moon or even asteroids or things like that helps us learn about the kind of ancient history of Earth.
Yes.
Because a lot of that has been kind of worn away from erosional forces.
Yes.
Right?
Yes.
Okay.
Absolutely. And one of the reasons we go to Mars is because Mars is like this weird amalgam of Earth and the moon. There definitely was water there. We see evidence of lakes and stream channels, maybe oceans, an ocean.
Wow.
Don't know.
Exciting to think about.
Yeah, right? It's very exciting to think about. But then it's also covered in a lot of craters.
Right.
So, and then so Mars' history, the rough Mars history is like Earth, 4 billion years ago, lots of impact craters. You probably have some water, liquid water on the surface. You have an atmosphere. 3 billion years ago, it kind of everything stops. Like everything gets cold. The atmosphere starts to go away. All that water gets locked up as ice. You start carving the planet. There's no plate tectonics, at least not. Maybe there's a little bit in the 4 billion year-ish time period, but then it all stops. So Mars is like a frozen picture of Earth from 4 to 3 billion years ago.
Wow.
You go to Earth, find me a 4 billion year old rock. You can't.
Right.
Maybe there's a zircon crystal that they've dated. Like, this is 4 billion years old. Cool. It's microscopic. And, it's amazing what scientists can do with that little zircon. They can tell you about temperatures and pressures and was there water or not.
And what is the oldest? Is it about 2 billion years?
No, there's some rocks that are in the 3 billion years old,
okay.
But they're like really grungy nices, like lots of Canadian Shield stuff. Some of that gets into 3 billion. There's some stuff in Australia as well. It's a little outside my geologic range. I mean, more so now, but back in Archaea and all that stuff. It's pretty grungy. It's not like on Mars. It's like, well, these sedimentary stack layers are 3.5 billion years old.
Wow.
On Earth, it's like, well, that grungy crunched up thing is those rocks, and I don't know what they were before, but now they're a bunch of metamorphosed crushite or just junk. I mean, it's not junk, but I mean it's highly deformed. You don't find a lot of stuff that's like in place. That's actually survived from that time period. It's all been reworked.
Right.
That's the Earth. So Mars. So that's where like your analogs. If you want to learn about early Earth, you actually go to Mars because that time period of geologic history is still there. But then things like transferring things over. So like let's take something different like volcanoes. Lots of volcanoes on Earth. You can study them. We've got these kind of Strombolian eruptions, kind of things with big fire fountains. And then you have things like Hawaii, these big, broad shield volcanoes, and lava comes out. It's really liquid and diffusive and just kind of makes these big pancake volcanoes. Mars, kind of see the same thing. Most of them are kind of pretty broad, though. We don't see a lot of these Vesuvius-type eruptions. We're mostly seeing these big, broad pancake. But the thing is, like, they're huge. I mean, Olympus Mons on Mars is 25 kilometers tall. I mean, it's I think it's still true. The biggest volcano in the solar system. It's this huge broad edifice and it has this weird like collapse features on the sides because it's so big and just like it warps the crust. I mean, in a way that you can actually see. It's really, the scale is immense. It's so, and in fact, it's so flat. If you landed like in the middle of the flank of the volcano of Olympus Mons and you looked, in either direction, you would think you're on a flat plane.
Wow.
It's so big and so flat. So it's just really, the scale of things change, partially because of gravity and partially because of like the composition of the magmas. They're like, they're a little more effusive, they're a little more liquid and just kind of just spread all over the place. And then you go to Io. Lots of volcanoes. We can see active volcanoes erupting today. It's always the amazing part. Like you can go, I mean, not with your regular telescope, but quote unquote good one. One that's like 10 meters wide or 5 meters wide. You can. Well, actually, I don't know if you can. Okay, I take that back. I don't know if you can see a plume eruption on Io. Maybe they're just around Jupiter. In case people are wondering. But anyway, every spaceflight flies by, they take a picture of Io, satellite of Jupiter. It's a completely volcanic planet. It's nothing but volcanoes and lava flows. That's it. No water, just that stuff. But all the lava is like very sulfur based. So you get volcanoes, you get these plumes, but then you get this like weird yellowish sulfur rich magmas, and they have different temperatures, and some of them are red and black, and it's because of the amount of, I think it's because of the amount of sulfur in the lava flows. And so it's just, it's volcanic, but like totally different from Earth. Like we don't get that same type of volcanism on Earth. So it's, so you have to like, you start with like, oh, it's a volcano, but it's really different chemistries. Or Titan is the other example. Titan, pretty cool, awesome moon of Saturn. Has a thick atmosphere like ours, all mostly nitrogen, which is pretty interesting. The surface, it's like water ice and a bunch of stuff that people call goo. They call it the goosphere.
This highly scientific term.
Highly scientific. Someone had a talk once at the Lunar Planetary Science Conference, and they call it the goosphere. It's all organics. It's like liquid methane and all sorts of, I don't want to say oil's the bad word to use because it's not really oil, but it's of that idea that's like it's all gooey organic stuff. But it's also super cold. So things that aren't normally liquids and solids are liquids and solids on Titan. So, they get sand dunes, but like it's sand in terms of size probably, but it's made of like tar balls or, the equivalent, like little tiny tar balls that really become sand. And so the lakes are liquid methane.
Right. Weird.
Like there's almost, from what they can tell, there's, because of the viscosity of the liquid methane, there's like almost no waves. They're really small. It's just a weird, there's a lot of things that are like karst, but it's, which is like limestone caves. Yeah. But it's karst of like, it's like ice karst. And, so it's like you like the temperature and like it's super cold. Oh, by the way, it's like minus 200 C or it's super cold. It's a completely different material acting in ways that we don't normally think about. I mean, because they're in a different state of matter, methane on Earth, it's like, it's a gas. There, it's liquids and solids, and it becomes a totally different, and they work a little differently because of different materials. Yeah. They're not the typical rocks that we're used to working. So you have to rethink everything. Yeah. You have to go back to your first principles, like, well, what if it was, what if this, instead of being like a bunch of basalt, it's actually a bunch of water ice? How does that change? And, and then Pluto's the other one. I mean, Pluto, which, is this fascinating world that's built out of nitrogen ice, and water ice and other, called tholins, which is another form of organic weird material, which we don't understand. It has nitrogen glaciers and nitrogen frozen beds. It's just so different. So you have to rethink, like, take all those things you understood about water and fluid movement on Earth, change the material, and then redo the calculation. So
you're constantly just having to shift things around, like a shell game almost.
Exactly. And like, there's no waves on Titan. Like, okay, well, how does that change how your sand deposits on the edge of a lake? Or and there are lakes, but it's not water lake, it's liquid stuff, organic. So so you really have to rethink everything. And even on Mars, which is close to Earth, you have your typical rocks. We get CO2 ice, and you get weird blocks sliding down sand dunes. And the other thing is like, the other thing is like Mars is, it's, we see features that are like lake sediments, but we get all these flat lying layers. And typically that's stratigraphy, and so, stratigraphers go out there and measure the angles of rocks. But it's like, it's those rocks, but they're also constantly being impacted over the lifetime of Mars because the atmosphere went away. So all those blocks are shifted. So how do you, what's flat? Like you see a rock with a bunch of flat lying layers, like, but is that their original position, or have they been moved? Right. And pretty much the answer is probably, they've probably all been jostled a little bit. And so you can't do the same things. Like you have to do these weird reconstructions of like, was that the original angle? Oh, I think that's in place. Is it? I don't know. Maybe, and so it becomes challenging to take your normal field methods and then apply them to Mars. Besides the fact that, we have this, kind of in relation to Earth, the soda straw of data that you get back. We only have one rover, and we can't drive it everywhere. And, the rocks we look at today means they're rocks we're not looking at tomorrow. So we do this trade between stay here for a week, or spend one day here and spend the next 5 days or 7 days looking at other places. So, so it becomes challenging,
And yet, it works.
Yeah, absolutely.
That's the crazy thing is like, even though all these kind of shifts in thinking that you're talking about you're constantly, okay, at least we know the materials, at least we know what these things are made of. That's at least a constant, it seems, what things are made of. But then the actual shifting of all of these, components, does seem to, we wind up with a net gain of information, absolutely, a huge net gain. train of information, which is the incredible part to me.
Yes.
Like, I mean, every time it's like, I keep hearing from scientists who work on this kind of stuff that even our failures, we're learning a ton, I mean, and we're failing less and less too, because we're learning so much, so that is just so, that I think is the coolest part, is like, we seem to be at a place where no matter what we do, we're going to learn something from it, which is super cool.
Yeah. And I think there's always I
say we.
Well,
if I'm doing the work.
No,
you're
absolutely,
out there doing the work. I'm like, hey, Fred, isn't it great that we're doing all this work?
If you're spreading the word, we're fine with that. You're part of the team. And I think that you tend to want to say, what's your metric for success? And a lot of people will say answers. I think the other metric is questions.
Yeah.
How many more questions do you have now? How many things did you not figure out, or not that you didn't figure out, but like, this one answer led to 10 more questions.
Yeah.
That's awesome, because that's what we want. We don't, scientists are the weird people. Like, we're not happy with perfect success. When we are, of course, we can go take the measurement, we get the measurement. Great. But it's what comes after that. What did that tell us? What did that tell us? Not only what we knew, but what we didn't know. And then we can explore that and just get deeper and deeper into the rabbit hole of science. It goes down and down and down and down, and there is no bottom, and we're totally cool with that. We're letting people like, was I wrong? Okay, cool.
Right.
Wow. Yeah. What should I have thought of? Or oh, that wasn't quite right. Okay, I'll rethink that, and it's okay. Yeah. Science is a weird, ephemeral thing. It's the mist that keeps making shapes, and then it deconvolves and reconvolves, and it's always evolving. And I think sometimes people don't get that. Like, scientists is not like a like the table. You build the table, it's a table forever. It's like, no, today it's a table, tomorrow it's a chair, the next day, it becomes your house. Or it evolves constantly, and we like evolution. We like things that change, and we're not happy with perfection. And we also realize, like, it's never gonna be perfect. We will never know everything, but we get always pushing towards that closer and closer.
Man, what incredible information. I mean, it's not just mind-boggling, it's also mind-blowing. It's just fantastic. So I wanted to know from Dr. Fred about how scientists like him respond to conspiracy theories. They're everywhere, as you know. Sure, a lot of them are silly. Others, get a lot of people to buy into them. And some of these conspiracy theories are rooted in the fact that in the past there have been hoaxes, and Dr. Fred even mentions that. There have been hoaxes by people who wanted something to be real, and they wanted to convince people it was. I mean, it's not like we're not familiar with this. I mean, if you've seen any quote-unquote Bigfoot footage, you'll know what I'm talking about. But that is not coming from scientists, or at least not the scientists of today. So I asked Fred, how do you handle that? What do you think about that? And really, what's at the core of people wanting to believe that everything they work on is completely phony or fake? To me, that would just drive me crazy. But Fred was far more gracious about it.
I think in a general sense, there's nothing wrong with anyone asking questions. Questions are good. That's what scientists do all day long. We ask questions. Asking questions is good. But you have to go beyond the ask questions. You have to go, what evidence or what things can I see that verify that question? And that's where I think, have there been conspiracies in the past? Absolutely. We can go down a laundry list of things that have happened that were underhanded and deceitful, or put forward as complete opposite of what was true. However, there's a cases where, I think there's like, I'll go like anthropology, like, what was it, Java Man? Or, there are people like constructed this things like, this is the last old fossil, and it was totally untrue. I think that just happens less because we've gone to this world where it's not just like someone standing up and saying, here's a skeleton. It's, here's a skeleton, here's my measurements I've made, here I've compared to other things. Like, science has become more of this like evidence building, and not just, we can all put out wild theories, which is fine, or questions which are challenging our understanding, but you have to back that up with evidence. And I think the only problem with people who do, say, flat Earth.
Right.
I was gonna say near and dear to my heart, the opposite. But we've known since 200 BC. I mean,
right.
The
using mathematics,
observation.
Yeah.
When the boats came over the Mediterranean to Greece, you saw the top of the mast, and then the rest of the mast, and then the boat.
Right.
What does that mean? Curvature. The experiments, and the classical one I like is the well. People look at when the sun's straight overhead at during the summer equinox. The sun's right overhead, it goes straight down into the well. Right. If you go so far away, it doesn't, because there's an angle, because the Earth is round. Like, so people have been able to measure the shape of the Earth and know it's round, even though they never went to space.
Right.
Just observation showed the Earth was round. We have satellites now, which have gone into space, and there you can see the full size of the Earth, that it's round. Now, it's interesting because people say, like, look, I went up on this plane and the Earth is still flat. It's like, okay, here's the experiment you got to do. Take a beach ball, right? Hold it out from your face, and it looks round. Now bring it to your face till your eyeball is almost on the surface. And what happens to that curvature? It gets flatter and flatter and flatter. Now imagine that beach ball is the size of the Earth. It's 6.7 million kilometers in radius, so it's about 12 million kilometers, something like that on Earth. I don't know, Earth, Mars, I can tell you. It's on Mars, it's 3,396,000.
Okay, that's the last of our song titles for Dr. Fred right there. That was Earth Schmirth. You might have heard it was me saying it this time and not Fred. Most of the titles came from phrases that he said, but Earth Schmirth just sounded great. And since his mind is usually on Mars, it just seemed quite fitting.
1,000 kilometers radius, but that's because, I study Mars. The joke with some of my friends is like, I say like, on Mars, I can tell you where that rock is down to the centimeter. On Earth, I can't find Sepulveda Boulevard. I don't know where it is. Like, where's that in LA? Like, where's Los Alamitos? I don't know. It's in LA somewhere. In any case, but the idea that so you imagine this really big ball, you get the close surface. Of course, everything becomes flat,
right.
And so it's like, to see the curvature of the Earth, you have to be in space. Right. You can't just be flying around anyway. So it's just like, and there's that somewhat movie that's come about flat Earth people and like what their perception is, but it's like some of them actually said like, well, if the Earth is flat, we do this experiment where we measure this laser beam shot out straight over this water, it would hit this height. If it's curved, then we'll expect the laser beam to be higher above your head. And so they do. Have you seen this movie on Netflix? It's a documentary about flat Earth conspiracy.
Oh, interesting.
So some people are like, we're going to approach it scientific method. Awesome. Do it. They do it. So they take the measurement, and it's like, so if the Earth is flat, the laser beam's going to hit them about eye height. If the Earth is curved with the distance that they're measuring over, the laser beam will hit above their head. And so towards the end of the movie, they do the experiment. And the guy, the person far, far away, is like, "Oh, I don't see the laser beam. Laser beam." And the guy's on the other end. He's like on a walkie-talkie. So like, raise the board up, and he puts it over his head. He's like, "Oh, I see it now." And the other guy goes, "Oh." And so they do a couple things like that. But then like so they think like, you would convert those people. And they go, "Oh no, that experiment didn't come out quite right. We have to do it again." It's like, that's okay too, to retest, but it's like, you've got to.
There has to come a point where if you're gonna go through the trouble of doing the experiment, and you have to, trust the results if it's being done correctly.
You have to believe your experiment.
Yeah.
And you can always, tons of times people look back at experiment and found errors, but your experiment told you something, and and then it becomes this, do you just believe on faith that the Earth is flat or is round, or do you actually have proof? And I think it's just, people, it's awesome to have questions. You have to, when you have counter evidence to the contrary, you have to be willing to change your belief system, your belief, right? The belief, but I think that's where science, like, it's not belief, because belief is just believing without evidence.
Yeah.
We require evidence. Thereby becomes hypothesis and theory.
Right.
And those get all backed up by evidence,
Yeah.
or they're rejected. That's the history of science. That's the way things work. So yeah, I don't know. So my experience with this, and because I'm a scientist, I actually answered the question. Random email. Hey, there's or maybe it wasn't an email. It was probably, something on the web, and someone pointed out like, oh, there's a lighthouse on Mars. Look, there's this flash of light from this same location, in the images from two different locations from the rover. And so we get a lot of like cosmic ray hits on the lenses, on the sensors for the lenses, and so you get like this light streak. But we do them from different locations, and thereby you're not going to get the same cosmic ray streak for the most part, statistically.
Yeah.
In this case, there was like light from pointing in more or less the same direction, and I was like, oh crap, what is that then? And so I said, well, let me calculate where those flashes would come from based on the rover position and the angle. And while the lights were roughly in the same direction, because I had because I could do the math to the distances, they were in completely different distances, and they didn't align. And so it's like, no, just weird statistical things, cosmic ray strike in the same location, because the other option would be like, oh, maybe that's a really flat, shiny rock.
Right.
And where you're just hitting the sun angle is just hitting it right. Perfectly valid, right? But didn't require you to build a Mars lighthouse.
Right.
And it's build a civilization and then a thicker atmosphere, like because you can say that, but then it's like, but what does that mean? Like if you're saying like there is a lighthouse, which means a structure that was built by some sentient being, you have to do the rest of the work. Like then there must be there had to have been a habitable atmosphere. There had people who grow. There had to be something that they ate. There had to be houses. They had to have had a reason to build the structure. Like it implies so much. Just say like, oh, I see a rat scurrying on Mars in that image. Like, you know what that means?
Right. Have you really walked this back?
Yeah. Walk that back. What does that mean? It means you had microbes, which became it became multicellular, that became a fish, which became a land animal, which grew hair and became a mammal. It's a huge thing. And to see one weird thing, but with so much backstory to it.
Right.
We don't see evidence for the backstory, so thereby it's probably just your eye thinking you see stuff.
And that probably becomes
that
probably really becomes hard to convince a person at that point, because once they've gone to lighthouse or rat or sentient being, then they've already got in their minds a story. And once they're attached to a story, it's hard to pull them away from that. And then you come along and say, no, it's just an anomaly. What are you hiding from us, Mr. JPL?
Yeah. Oh yeah. Okay. So I'm kind of here in my own personal time. I don't speak for NASA.
Right.
But let me tell you my personal story about that possibility. No freaking way. If we saw anything which remotely looked like a living creature or thing, there's no way. Right. It would be out in a second. People are human.
Yeah.
People are scientists are like,
people leak movie plots.
Right.
Scripts.
Exactly. That's right. The most banalest of things, right? I mean, sometimes it would be out. I mean, you already know, or like I just said earlier, the gravitational experiment, like that got leaked in someone's cake, made a celebratory cake. Like
Here, Fred is referring to something he told me about before the mics were rolling. It was an incident where the scientists were going to keep things under wraps until they announced it to the press. It was about gravity waves, but they had made a little cake to celebrate this discovery, the observational evidence for it. And somebody took a picture of the cake, and it went up on Twitter before anybody else knew about it. And so even something as important as gravity waves was leaked via Twitter because it was on a cake. So his point being that it is incredibly difficult to keep new information away from the public.
That stuff would be plastered all over the place. There's just no way it just, and the fact is thing is like, well, I know this is like saying like, well, we bunch of all the photoshopping team on NASA is busy at work all day, but the irony of that is like, well, we don't,
right? For starters.
B, there are days and frequent time periods we release the images coming down from Mars to our public website before any scientist has seen it.
Yeah.
That is the absolute truth. Mm-hmm. So if there was a rat in that image, the only reason you're seeing the thing you think is a rat on Mars is because we released that raw image frame out to the public service.
Yeah. And my final question for Dr. Fred was about what was something that truly just blew his mind? Because all of this stuff is amazing to me, but for it to be mind-blowing to a scientist, what is that thing? What does that have to be? What was that moment, that discovery that really shook him? And I was really fascinated by his answer because it's a reminder of a lot of this stuff is, we've come to accept it now. We know this about Mars. We know about stream channels. We know about, these erosional features and water and liquid moving across the surface. But there was a time where that was not the case at all. And that is where he began his answer.
Everything, a lot of things on Mars are put down by water. Mm-hmm. And in Gale Crater, especially so, there's lots of lake sediments, there's lots of river channels, and when we first landed, we landed in this flat area which looked pretty nondescript and not a big deal. There are these huge thick conglomerates which were like the beds of old stream channels, and the water was up to your knee, and because we tell because of how rounded, we literally we looked at the rocks, and they're like all these little round centimeter sized pebbles, and we're like, oh, that's cool. We didn't see that from more. We weren't expecting that at all. I mean, zero.
Really?
We did not. I mean, I suppose if we had thought about it, we might have said, well, we'll find some kind of water laying down rocks. Maybe, but not that. Wow. Not exactly that. And so that
shows evidence of a lot of water, correct?
Yeah. Oh, like I said, knee height water, we landed in a place where had it been 3.5 billion years ago, we would have been up to the rover deck in water, right? Or something the equivalent of that. Or the wheels would have been covered in water and water racing by and sand, going in between. So
it would have been a splashdown.
Oh yeah. Yeah. I mean, it just no one expected that, and that was something just incredible. That was a thing you can't see from orbit.
Yeah.
Right.
Yeah.
So told us that was brand new. That was amazing, and that was like, yes, we picked the right place. And a lot of times, like right now, where we land is really guided by the chemistry of the rocks, and so we have CRISM, which is a compact reconnaissance imaging spectrometer, which big fancy word for saying we take pictures of rocks in lots of colors beyond our visible spectrum, really into the infrared, and we can tell what the chemistry of those rocks are.
Right.
So the places where we saw really interesting rocks, water laid down rocks, was near Mount Sharp, clays and things we expect, and sulfates, which generally have some water in them. Like that's where we wanted to go, but we landed like 10 kilometers away because we have to drive there. We didn't know what was underneath our feet. Yeah. Chemically. But when we got down there, so the rounded pebbles were like, oh, that's water. Wait, that's deep water. Oh, that's water on the surface. That's, thick atmosphere. It's not frozen. It's flowing water. It just, your brain starts to explode and like, okay, this is a different planet. This is not a lava planet. This is a water planet. At that time period.
Huge shift then in thinking.
Yeah. And so then, instead of looking through the lens of the volcanologist, we're like, oh, that's a lava flow, or that's a kapuka, or blah, blah, blah. No, that's lake sediments. That's solidified, sand from some water depositions, and so on and so forth. So just you change your scope of like what you really see and what you think you see, and and expand the possibilities. So that I think to me is like water was everywhere in Mars. Mars was a wet planet. Varying degrees in varying areas, and sometimes it was a cold, wet planet. Glaciers are ice-covered lakes, but still liquid water on the surface at some point. Something like Gale Crater. So we measured that. We went to Yellowknife Bay, which was near where we landed, which we did not expect to do. We expected to land and run to the mountain. Instead, we were like, oh, that area over there, that kind of looks like lake sediments. That looks like what a lake would look like if it had bottoms at the bottom. Let's go there first. Drove 200 or 300 meters, down the block per se, and made our first 2 drill holes and found, it was a lake. What's even cooler is it was a lake that was like water that comes out of your faucet. Pretty neutral pH, filled with all sorts of the goodies that microbes would like. If there was life, if I said that word, if, not in quotes, but if there was life in the past and it was in that lake, it'd have been super happy. It had liquid water. It had it had good temperatures. It had good pH. It had the chemistries it would want to eat stuff, or to at least metabolize of some form. Right. Super awesome.
Yeah.
None of that we knew from orbit.
Wow. Yeah.
So, it was like, because always missions have a certain lifetime, and ours, the prime mission, where you want to do all the big things, was 2 years. We solved it in less than a year.
Wow.
We met that requirement in less than a year.
Yeah.
Which just amazing.
Yeah.
And then we change. Then it changes how you look at everything in that planet.
Oh my gosh, it's just ear candy for a planetary science geek. This is just gold, or iron, as the case may be. Lots of iron and oxygen. On Mars, the red color. Yeah, sorry, the jokes don't get any better than that on this episode. That's a really awful science joke right there. Does that even qualify as a science joke? I don't know. It's more of just a bad statement, but I'm going to own it. My huge thanks to the amazing Dr. Fred Calef and the incredible work that he has done over the years, and his just willingness to share the process, and not only with us, but with others. He's always at multiple outreach and educational events for the public. Of course, he does great work at JPL, Jet Propulsion Laboratory here in Southern California, but he also uses any opportunity to communicate that with other people, and we greatly appreciate that. One final note I will say is the man can also wear a T-Rex costume like nobody else. We didn't have time to get into it in this episode, but if you check out his Twitter account and you go back to around Halloween, you'll see what I'm talking about. So, he basically was in the costume contest at JPL and just simply wore one of those inflatable T-Rex costumes. But because he was using his little T-Rex arms to, sign his autograph and things like that, it kind of took on a life of its own. And even though people had more complicated costumes, the T-Rex, the Dr. Fred T-Rex became quite the sensation in October of 2019 there at JPL. So, and I'm assuming that means he's going to make a comeback in the future. So, keep an eye out for that. If you see any information about T-Rexes at JPL, you'll know that Dr. Fred might be one of them. So again, my huge thanks to Dr. Fred Calef, and with that fantastic interview, now in 2 parts, our first 2-part podcast episode, ladies and gentlemen. So thank you to Dr. Fred for sitting with me for that long to answer all those questions. So we had enough material for 2 episodes. And of course, at the end, I asked him, as I do all the scientists and guests I interview, would he introduce the song for this episode, the epic Geology Folk Song Medley? And he said no. I'm totally kidding. He said yes. Of course he said yes. He's just that kind of a guy. So here, one last time, is Fred Calef.
Hi, this is Dr. Fred Calef III, and next you're going to hear Geology Folk Song Medley by the Amoeba People.
All right, let's do it once more because I forgot I turned down your mic when you were doing the theremin.
Rude.
All right, we're rolling. You're good.
This is Dr. Fred J. Calef III, and now you're going to hear Geology Folk Song Medley by the Amoeba People.
Woo!
Yeah!
Thank you.
Thank you. Thank you. Oh, my stars.
Thank you, folks. Thank you. Meandering river, you roll on down the plain, eroding and unloading the rocks that you find until you make an oxbow lake. You know where you're going, where gravity's inclined. Just look at all the wonders that you leave behind, meandering river and time. Empty tents in the valley, where did those geologists go? Are they up on the cliff,
We're down in the schist.
or floating in that river below? Empty tents in the valley, where did those geologists go? Empty tents in the valley, we may never, ever know. There once was a girl that I courted, and I called her my tailless slope. I thought she was my one true love, but she left me and called me a dope.
There once was a girl that he courted, and he called her his calastic wedge. But his geologic term of endearment finally sent her over the edge. You gotta dig it deep,
Dig it deep,
dig it down to the pith.
down to the pith.
If you wanna get down
Wanna get down
to the batholith,
to the batholith.
it's like a giant blimp
It's like a giant blimp,
in the crust of the planet.
crust of the planet.
But you've never seen a blimp
Never seen a blimp,
made of rock solid granite.
rock solid
You
granite.
gotta dig it deep,
Dig it deep,
dig it down to the pith.
down to the pith.
If you wanna get down
Wanna get down to the batholith. When our earthly time has run and we face life's setting sun, we're rolling to the outcrop in the sky. My oh my, we might erode or crystallize, or subduct and orogenize, or just roll on to the outcrop in the sky. Well, it's a mighty fine hammer ringing through the canyon. Well, it's a mighty fine hammer ringing across the land. Well, it's a mighty fine hammer ringing from the mountain, ringing out to every woman, child, and man. No, we're not going home.
No, we're not going home.
No, we won't be moved.
We won't be moved.
Keep chipping away.
Chipping away.
We got something to prove. No, we won't be satisfied. We'll hammer around the clock until we learn that mineral composition of the rock. Until we learn that mineral composition of the rock. Until we learn that mineral composition of the rock.
Thank you so
Thank you.
much. Oh,
What
my
about this marvelous gal here?
goodness. Thank you. Thank you.
Isn't she great? Thank you.
And thank you for listening to the Amoeba People podcast, where science and music collide. I love that laughter at the end of that song right there. That's Ron Butler Jr. My thanks to him, and my thanks to Lisa Bodie Hurd, the female vocalist that you hear on that song as well. Two great friends of ours who have helped make Geology Folk Song Medley the song that it is, or the songs that they are. That song appears on the Fossil record, our most recent album, so check that out. You can find that everywhere. It's on Spotify. You can download it through Bandcamp or Apple Music. pretty much anywhere you want. If you're out of the country, we learned that Deezer is a big thing. So I'm pretty sure, I know this podcast is on Deezer. Hopefully our music is too. I don't know quite how that works. Let us know, though. You can email me at ray@m51records.com and let me know. Like, we want to hear from you guys, okay? So hit us up. Talk to us. You can also find us on social media. We're real easy to find on Instagram. That's probably the best place. Facebook as well. And thanks again to all of you guys for tuning into our show. We really appreciate it. We've got some exciting things coming up in 2020, so stay tuned. Be listening to this podcast for details about all those things coming up. And of course, if you want to support our show, please give us a rating on whatever platform you download podcasts. Until next time, onward!